Welcome back. Last time we aborted the study of public key encryption, and we said what a public key encryption scheme was in terms of syntax. We gave definitions of a metric of security, IND-CPA, and we gave an example of how you build such a scheme based on the hardness of the computational Diffie-Hellman problem, which is effectively that of the discrete log problem. Today we're going to turn to a different and very popular public key encryption scheme, which is RSA. Before we get into the math, let's start with a video which illustrates this informally.
Up until the 1970s, cryptography had been based on symmetric keys. That is, the sender encrypts their message using a specific key, and the receiver decrypts using an identical key. As you may recall, encryption is a mapping from some message using a specific key to a ciphertext message. To decrypt a ciphertext, you use the same key to reverse the mapping. So, for Alice and Bob to communicate securely, they must first share identical keys. However, establishing a shared key is often impossible if Alice and Bob can't physically meet, or requires extra communications overhead when using the Diffie-Hellman key exchange. Plus, if Alice needs to communicate with multiple people, perhaps she's a bank, then she's going to have to exchange distinct keys with each person. Now she'll have to manage all of these keys and send thousands of messages just to establish them. Could there be a simpler way? In 1970, James Ellis, a British engineer and mathematician, was working on an idea for non-secret encryption. It's based on a simple yet clever concept. Lock and unlock are inverse operations. Alice could buy a lock, keep the key, and send the open lock to Bob. Bob then locks his message and sends it back to Alice. No keys are exchanged. This means she could publish the lock widely and let anyone in the world use it to send her a message. And she now only needs to keep track of a single key. Ellis never arrived at a mathematical solution, though he had an intuitive sense of how it should work. The idea is based on splitting a key into two parts, an encryption key and a decryption key. The decryption key performs the inverse or undo operation which was applied by the encryption key. To see how inverse keys could work, let's do a simplified example with colors. How could Bob send Alice a specific color without Eve, who is always listening, intercepting it? The inverse of some color is called a complementary color, which when added to it produces white, undoing the effect of the first color. In this example, we assume that mixing colors is a one-way function because it's fast to mix colors and output a third, and it's much slower to undo. Alice first generates her private key by randomly selecting a color, say red. Next, assume Alice uses a secret color machine to find the exact complement of her red, and nobody else has access to this. This results in cyan, which she sends to Bob as her public key. Let's say Bob wants to send a secret yellow to Alice. He mixes this with her public color and sends the resulting mixture back to Alice. Now, Alice adds her private color to Bob's mixture. This undoes the effect of her public color, leaving her with Bob's secret color. Notice Eve has no easy way to find Bob's yellow since she needs Alice's private red to do so. This is how it should work. However, a mathematical solution was needed to make this work in practice. The solution was found by another British mathematician and cryptographer, Clifford Cox. Cox needed to construct a special kind of one-way function called a trapdoor one-way function. This is a function that is easy to compute in one direction, yet difficult to reverse unless you have special information called the trapdoor. For this, he turned to modular exponentiation, which we introduced as clock arithmetic in the Diffie-Hellman key exchange, as follows. Take a number, raise it to some exponent, divide by the modulus, and output the remainder. This can be used to encrypt a message as follows. Imagine Bob has a message which is converted into a number, m. He then multiplies his number by itself e times, where e is a public exponent. Then he divides the result by a random number n and outputs the remainder of the division. This results in some number c. This calculation is easy to perform. However, given only c, e, and n, it is much more difficult to determine which m was used because we'd have to resort to some form of trial and error. So this is our one-way function that we can apply to m, easy to perform but difficult to reverse. It is our mathematical lock. Now, what about the key? The key is the trapdoor, some piece of information that makes it easy to reverse the encryption. We need to raise c to some other exponent, say d, which will undo the initial operation applied to m and return the original message m. So both operations together is the same as m to the power of e, all raised to the power of d, which is the same as m to the power of e times d. E is the encryption, d is the decryption. Therefore, we need a way for Alice to construct E and D, which makes it difficult for anyone else to find D. This requires a second one-way function which is used for generating D, and for this, he looked back to Euclid. Over 2,000 years ago, Euclid showed every number has exactly one prime factorization, which we can think of as a secret key. It turns out that prime factorization is a fundamentally hard problem. Let's clarify what we mean by easy and hard by introducing what's called time complexity. We have all multiplied numbers before, and each of us has our own rules for doing so in order to speed things up. If we program a computer to multiply numbers, it can do so much faster than any human can. Here is a graph that shows the time required for a computer to multiply two numbers. And of course, the time required to find the answer increases as the numbers get larger. Notice that the computation time stays well under 1 second, even with fairly large numbers. Therefore, it is easy to perform. Now compare this to prime factorization. If someone told you to find the prime factorization of 589, you will notice the problem feels harder. No matter what your strategy, it will require some trial and error until you find a number which evenly divides 589. After some struggle, you will find 19 times 31 is the prime factorization. If you were told to find the prime factorization of 437,231, you'd probably give up and get a computer to help you. This works fine for small numbers, though if we try to get a computer to factor larger and larger numbers, there is a runaway effect. The time needed to perform the calculations increases rapidly as there are more steps involved. As the numbers grow, the computer needs minutes, then hours, and eventually it will require hundreds or thousands of years to factor huge numbers. We therefore say it is a hard problem due to this growth rate of time needed to solve it. So factorization is what Cox used to build the trapdoor solution. Step 1. Imagine Alice randomly generated a prime number over 150 digits long. Call this P1. Then a second random prime number roughly the same size. Call this P2. She then multiplies these two primes together to get a composite number n, which is over 300 digits long. This multiplication step would take less than a second. We could even do it in a web browser. Then she takes the factorization of n, P1 times P2, and hides it. Now if she gave n to anyone else, they would have to have a computer running for years to find the solution. Step 2. Cox needed to find a function which depends on knowing the factorization of n. For this, he looked back to work done in 1760 by Swiss mathematician Leonhard Euler. Euler continued to investigate properties of numbers, specifically the distribution of prime numbers. One important function he defined is called the phi function. It measures the breakability of a number. So, given a number, say n, it outputs how many integers are less than or equal to n that do not share any common factor with n. For example, if we want to find the phi of 8, we look at all values from 1 to 8. Then we count how many integers 8 does not share a factor greater than 1 with. Notice 6 is not counted because it shares a factor of 2, while 1, 3, 5, and 7 are all counted because they only share a factor of 1. Therefore, phi of 8 equals 4. What's interesting is that calculating the phi function is hard except in one case. Look at this graph. It is a plot of values of phi over integers from 1 to 1,000. Now, notice any predictable pattern. The straight line of points along the top represent all the prime numbers. Since prime numbers have no factors greater than 1, the phi of any prime number, p, is simply p minus 1. To calculate phi of 7, a prime number, we count all integers except 7, since none of them share a factor with 7. Phi of 7 equals 6. So if you were asked to find phi of 21,377, a prime number, you would only need to subtract 1 to get the solution, 21,376. Phi of any prime is easy to compute. This leads to an interesting result based on the fact that the phi function is also multiplicative. That is, phi a times b equals phi a times phi b. If we know some number n is the product of two primes, p1 and p2, then phi of n is just the value of phi for each prime multiplied together, or p1 minus 1 times p2 minus 1. We now have a trapdoor for solving phi. If you know the factorization for n, then finding phi n is easy. For example, the prime factorization of 77 is 7 times 11, so phi of 77 is 6 times 10, 60. Step 3. How to connect the phi function to modular exponentiation. For this, he turned to Euler's theorem, which is a relationship between the phi function and modular exponentiation as follows. M to the power of phi n is congruent to 1 mod n. This means you could pick any two numbers such that they do not share a common factor. Let's call them m and n. Say m equals 5 and n equals 8. Now, when you raise m to the power of phi n, or 4, and divide by n, you will always be left with 1. Now, we just need to modify this equation using two simple rules. First, if you raise the number 1 to any exponent k, you always get 1. In the same way, we can multiply the exponent phi n by any number k, and the solution is still 1. Second, if you multiply 1 by any number, say m, it always equals m. In the same way, we can multiply the left side by m to get m on the right-hand side. And this can be simplified as m to the power of k times phi n plus 1. This is the breakthrough. We now have an equation for finding E times D, which depends on phi n. Therefore, it's easy to calculate D only if the factorization of n is known. Meaning D should be Alice's private key. It's the trapdoor which will allow her to undo the effect of E. Let's do a simple example to see all of this in action. Say Bob has a message he converted into a number using a padding scheme. Let's call this M. Then Alice generates her public and private key as follows. First, she generates two random prime numbers of similar size and multiplies them to get n, 3,127. Then she calculates phi of n easily since she knows the factorization of n, which turns out to 3,016. Next, she picks some small public exponent e, with the condition that it must be an odd number that does not share a factor with phi n. In this case, she picks e equals 3. Finally, she finds the value of her private exponent d, which in this case is 2 times phi of n plus 1 divided by 3, or 2011. Now, she hides everything except the value of n and e, because n and e make up her public key. Think of it as an open lock. She sends this to Bob to lock his message with. Bob locks his message by calculating m to the power of e mod n. Call this C, his encrypted message, which he sends back to Alice. Finally, Alice decrypts his message using her private key, D, accessed through her trapdoor. C to the power of D mod n equals Bob's original message M. Notice that Eve, or anyone else with C, N, and E, can only find the exponent D if they can calculate phi n, which requires that they know the prime factorization of n. If n is large enough, Alice can be sure that this will take hundreds of years even with the most powerful network of computers. This trick was immediately classified after its publication. However, it was independently rediscovered in 1977 by Ron Rivest, Adi Shamir, and Len Edelman, which is why it's now known as RSA encryption. RSA is the most widely used public key algorithm in the world, and the most copied software in history. Every internet user on Earth is using RSA, or some variant of it, whether they realize it or not. Its strength relies on the hardness of prime factorization, which is a result of deep questions about the distribution of prime numbers, a question which has remained unsolved for thousands of years.
Okay, a pretty engaging video, I think, even if a little bit long. It took us through a physical way to do public key encryption with colors, then gave us background in number theory and talked about what, as he said, is the RSA system. He described it as originating with Cox and Ellis, who discovered it independently of RSA in the British security services. Rivest, Shavir, and Edelman got the Turing Award for RSA some time ago. The video also gave us a nice illustration of computational difficulty, multiplication versus factoring, which is the basis of security. So now we're going to go through the math ourselves in some careful detail and arrive at the RSA one-way function. The math is quite simple. Again, it's engagingly interesting how little sophistication in number theory you need just from a basic algebra course to get here. When we worked with the discrete log problem, our main example was the group of integers modulo a prime. So z star p, where p is a prime. For RSA, there'll also be a number, but it'll be a composite number, which we'll denote by n. So we'll be looking at zn star as the main domain. This is a set, a finite set, and has a certain size. Recall it's the set of all integers that have no common factor with n, and thus exactly what's its size isn't evidently jump out at you. So mathematicians give it a name. They call that size the phi function of n. So phi of n is the number of points in the set zn star. Now, suppose I give you a pair of points E and D. To what domain do they belong? Well, phi of n is itself an integer. I can look at the integers modulo phi of n and relatively prime to it, which is this set over here. I'm going to take 2 points in that space, which is different from the space zn star. I choose them so that if you multiply them, you get back 1 modulo phi of n. I know that's possible because if E belongs to this set, since this is a group under multiplication mod phi of n, E has an inverse. And that inverse is exactly the D satisfying this equation. So I'm just saying I pick a point E in here and I let D be its inverse. Now we jump back to the other group. We take a point X in the group Zn star. One of the elements of RSA is this interplay between two groups, Z star phi of n and Z star n. In this group X, Zn star, I raise X to the power E, which I think of intuitively as encrypting it. And then I take the result, which I take mod n, not mod phi of n, but mod n, and raise it to the power d. Perfectly legitimate operations. And the claim here is that what will come back is just x itself. Raising to the e'th power and then raising to the dth power reverses itself, and you just get back the same thing you started with. The proof is quite simple. Look at what happens if I take x to the ed in the group Zn star. Now, remember that phi of n is the size of that group, the size of Zn star. Also remember by our study of computational number theory that you can always reduce the exponent modulo m, where m is the size of the group. There was a little fact about that. So it's always okay to write a mod phi of n up here. Whether I write it or not does not change the result mod n. When I write it though, I see from this equation that it's just going to be 1. So I get x to the 1, which is x. Again, remember all this is mod n. Okay, why have we done this? Because we have created something where we have one operation to encrypt and a different operation to decrypt. So let's define a function f parameterized by a choice of n, which we call the modulus as an integer, and another integer e we call the encryption exponent. And the function maps from Zn star to Zn star and is defined in a very simple way. On input x, just raise x to the power e mod n and return it. You can compute that using our mod x algorithm. Now, suppose that there is a value d in z star phi of n, such that e times d is 1 mod phi of n. Whenever e is itself in z star phi of n, then such a value exists. We call that the decryption exponent. The claim we had on the prior slide can now be restated as saying that if you consider the function f inverse, which on input y takes y and raises it to the power d mod n, then this function reverses f. Indeed, it is the inverse as the notation implies. And that implies that f is a permutation on Zn star, a one-to-one onto map. And the proof is simply the prior claim. If I take f of x, that's x to the e, and then I apply f inverse, that means by definition I raise it to the d. Well, the prior claim says we get back x. So we have f inverse of f of x is always x, which means that f inverse is indeed the inverse of f. Now, from the cryptographic perspective, the idea is that f is encryption and f inverse is decryption. We haven't said anything about security yet, but already something interesting emerges, which is that you encrypt using E and decrypt using D, which are two different keys. So let's look at an example of this. So suppose we choose as modulus the number n equals 15. What is Zn star? All numbers between 1 and 14 that have no common divisor with 15. So I write down all numbers from 1 through 14. I throw away what? Anything that's a multiple of 3 or 5. And I'm left with these things over here. What is phi of n? The number of things in here. So 1, 2, 3, 4, 5, 6, 7, 8. And now what is z star phi of n? Well, I look at all numbers between 1 and 7 and throw away anything that has a common divisor with 8. But that just means I throw away any even number. So what's left is 1, 3, 5, 7. So there are 4 points in here. And that's the setup for RSA. The next thing to set it up is I need to pick a number e in z star phi of n. Anything will do. I happen to choose 3. Then d has to be obtained in a very specific way. It has to be the inverse of e in this group over here. So D times E has to be 1 modulo 8, not mod 15, but mod 8. It turns out that what works is D equal 3, because 3 times 3 is 9, which is 1 mod 8. From an example perspective, it's a little unfortunate that E and D are the same, but I'd have to get to pretty large numbers to avoid that, so we'll live with that. Now, what is the RSA function? On input x, it returns x cubed mod 15, x to the power e modulo n. Note again, this is mod 15, this was mod 8. This function maps from z star 15 to z star 15, so it takes inputs in this set and returns outputs in that set. The decryption function g of y is y to the power d mod 15, which in this case is y cubed mod 15. To see that these functions reverse each other, we could compute them. So for any x, here is listed the value of f of x. 1 cubed is 1, 2 cubed is 8, 4 cubed, we have to do it mod 15. So 4 times 4 is 16. 16 mod 15 is 1, and 1 times 4 is 4. So we get 4. 7 cubed mod 15. So 7 times 7 is 49. Mod 15 is 4. 7 times 4 is 28. Mod 15 is 13, I hope. Anyway, you can figure all those out. What happens when you apply g to f of x? Well, you're taking whatever is here and cubing it mod 15. If you do that, you notice that this column is identical to this column, and that's what it means that the two reverse each other. So here's a little exercise to play with that type of stuff. When we set up RSA for usage, what we do is that the public key will be the modulus n and the encryption exponent e. The secret key will be the same modulus n and decryption exponent d. Now, it's only d that's really secret. The modulus n is in both places, but formally it's useful to think of the modulus as part of the secret key. Once that's done, encryption under the public key says think of x as the message and simply raise it to the power e mod n. And that was what we call f of x. Here we think of x as being in z n star. To decrypt a received ciphertext y, raise it to the dth power mod n, and you'll recover y. We sometimes use the term encryption for this, but more precisely what RSA is what's called a trapdoor one-way permutation. What do those different words mean? Permutation, because it's a one-to-one onto map, Zn star to Zn star. Trapdoor refers to D. You can compute it in the forward direction knowing n and e, and then given the trapdoor D and also given n, you can go backwards. One-wayness refers to the fact that if you don't know the trapdoor D, you would actually have a hard time going backwards, meaning given y, if I ask you what y to the d is, but I don't actually give you d, although it's mathematically uniquely defined through n and e, you would have a hard time actually computing it if things are set up right. As we've seen with other number theoretic systems, the math alone isn't enough. We also need algorithms to set the whole thing up. I have to create RSA keys on my system. So how do I do that? We encapsulate things in what we call an RSA generator. So this is an algorithm, and it has associated to it a security parameter, which is an integer k, indicating how much security you want. If you run this algorithm, it's a randomized algorithm, and it will return a whole bunch of stuff. There's a modulus n, there's a pair of primes p and q, and there's an encryption exponent e and decryption exponent d. And they're supposed to satisfy certain conditions, and if those conditions are met, we say this is an RSA generator. Now, here I'm not giving you a particular recipe or algorithm for a particular generator. There are many specific ways to return these 5 numbers satisfying these conditions, and different implementations will make different choices. What are the conditions? P and Q have to be distinct odd primes. The modulus n is simply their product. This tells us that although the math applies whenever n is any number, in fact, in practice we use it for n a product of two primes for security reasons. How does the security parameter k enter? It's the bit length of the modulus, or arithmetically, the modulus is in the range 2 to the k minus 1 to 2 to the k. The larger k is, the more security we have. E is required to be in this set. It's in Z star phi of n, not n, but phi of n. D is also required to be in the same set, and they're required to be inverses of each other mod phi of n. So all this is set up for exactly the math we saw. We can look at how this plays out in various places. You can go on the internet and build RSA keys. That means that somewhere underlying this, a generator is being run and it's producing these keys. For example, if I wanted 2048-bit key, I can click generate and it will give me keys. And I can copy these keys and then put them into my system or my web page and start using them. We can look at the math in a little more detail over here. So this guide sort of walks you through all the different elements of what we just did. So it says, give me some primes and I'll compute something, an RSA system as a product of them. So let's see, suppose I try 11 and 17 as my primes. So I set those and it says P times Q is 187. Indeed, that should be what I get by multiplying these two. It also computes P minus 1 times Q minus 1. Now we haven't done that math yet, but it turns out that that's phi of n. So R is phi of n, and it turns out to be 160. What's the next step? We need to find an encryption exponent and a decryption exponent. So it's going to help us do that by giving us a list of numbers which are 1 modulo R. Why is that? Because E times D is 1 modulo R. So if we take one of these numbers and see it as E times D, then we're done. We have a proper choice of E and D. Trying to see this number E times D effectively asks us to factor it. So let's see if we can factor the first choice, 161. What does it say? It says it's 7 times 23. Great, we did it. So 7 could function as E, and then 23 would function as D. Are there other things that it works? Let's try the next one. 321, factor it. 3 times 107, another couple of choices. I don't know if we'll get one that ever fails. We'll see. Let's try a big one, 3681. See, and now we see something different. Here, we get 3 factors. So maybe we could try to use this, but then we would have, let's say, E being this part and D being that part. And those look rather big. So let's go back to something simpler. 3 times 107. So let's use those as our choices of E and D, 3 and 107. Okay, and then it says check them. So E is 3, now D is 107, N is 187, phi of N is 160, E times D mod phi of N is indeed 1, and we're all set. So now it'll allow us to encrypt. So I need to take a message which has to be in Zn star. So how about 102? Let's see, what was N again? N was 187. We need something relatively prime to that. So let's see, I don't know if it works. So this is the result of raising that to the eth power, which means 3 mod n. And indeed, when you decrypt, meaning you raise 170 to the power 107 mod n, you get back 102. Okay. So how did they do that? How did they build that web page? How did they get that generator? So we'll talk a little bit about that and then move on to security. This is the fact that we kind of saw appear on the web page. It would be useful in all of this to have some better way of calculating phi of n than just listing the elements of Zn star and counting how many there are. And this gives a formula. It says if n is the product of two distinct primes, you can get phi of n by just multiplying p minus 1 and q minus 1. So for example, if n is 15, factor it as 3 times 5. And then this says that phi of 15 should be 2 times 4, which is 8. This is an example we did on the prior few slides. So if you go back and check, indeed z star 15, if you list it, is this. And if you count, there really are 8 things in it. So we haven't proved the formula, but we're illustrating it. It's sometimes useful to have a generalization of this. So if n has more than 2 factors, in general it factors as the product of prime powers, p1 to some power alpha 1, p2 to some alpha 2, where all the pi's are distinct primes and the alpha sub I are positive integers, then phi of n is the formula here. And you can see that our prior slide formula is just a special case of this when n is equal to 2 and alpha 1 equals alpha 2 equals 1. You can use this like if you want to find phi of 45, you factor it as 9 times 5 or 3 squared times 5, and then according to the formula it's 3 to the power 1 times 3 minus 1, 5 to the power 0 times 5 minus 1, which is 24. We're going to need this moving on, so let's just recall that we had this mod inverse algorithm. If you give it any number e and that number belongs to z star something and you also give it the something, it returns the modular inverse. So in particular, if I have e and z star phi of n and I run mod inverse on e and phi of n, I will get back d. So this says that once I've chosen e, there's a simple way to compute d. But the important thing to remember is that to do that, you need to know what phi of n is. You cannot just run this on e alone, you need this second argument. Other things we'll need for setting up RSA generators, we need to test primality, and we need to know that random numbers have a good chance of being prime, all things we've seen before. So here's how we might build one example of an RSA generator out of many. So let's choose e equal 3 for efficiency, because the smaller e is, the faster encryption is. We'll refer to the generator as KRSA3, and it'll have a security parameter k. How does it work? It needs to pick primes and a modulus, but it needs to ensure that 3 belongs to z phi of n star. So what does it do? It picks some random numbers, and it's trying to find primes which are roughly k over 2 bits long. So that way they'll have equal length, and their product is the candidate value of the modulus n. M is the candidate value of phi of n. Remember, that's the formula for it. But these are all candidate values because we don't yet know if these are prime, so we can't stop there. So we stop if P and Q are indeed prime, which we know how to test. If the GCD of E and M, E is just 3 here, is 1, which says that E belongs to Z star phi of n as we like. And this makes sure that the bit length of n is indeed k. Once we get this, we need the decryption exponent, which we get by the modular inverse algorithm as per the prior slide applied to E and to phi of n. And that gives us all our 5 quantities and we can return them. Again, there's many other choices of such generators. The main security attribute we want to study is one-wayness. Before we do that, let's look at one more interesting element about these generators. So if you look at standards for public key encryption and usage of RSA, you'll often find that they use this particular encryption exponent, 65537. And why? Well, here's someone on Stack Exchange who had that same question. It says, effectively asking, why should we use that? It says, The RFC, which is the standard, says the RSA exponent should be this. Why is it recommended, and what are the theoretical, practical impacts and risks of making the number higher or lower? So that's an interesting question, and indeed you might think that the answer has something to do with some security attributes, but there isn't a lot, at least if you use RSA properly, that isn't necessarily true. Now, there are some attacks on small exponent RSA, but usually things are set up to avoid them. So the real reason, let's do the following. Take this number 65537 and express it in binary. So take a decimal to binary converter. Let's type 65537 and see what we get. And what you see here is that this is a number which begins with a 1, ends with a 1, and has all zeros in between. Why have they done that? Well, the answer is that if you go back and look at the modular exponentiation algorithm, you'll see that it performs 2 group operations or multiplications per loop when the bit in the exponent is 1 and just 1 when it's 0. In other words, the more zeros in your exponent, the faster modular exponentiation runs. So this in particular is a way to make things run faster.